Hello, how are you doing? If you're actually watching this during the fall, I guess you're probably doing your pumpkin thing. Is that? But I guess that's when September, as soon as the fall starts, like you got to put pumpkins in everything, right? Yeah, pumpkin in your lattes and in your cereal, and whatever you want to put in, wherever you like putting your pumpkins, put them wherever you want. There are a couple reasons why I do this thing at home, and this is one of them. Pumpkin. All right. I've even seen pumpkin flavored dog treats. I don't think the dog gives a crap about this time of year, does he? I don't know. In lieu of kids for some people, huh? All right. So this week we are going to look at, for the general one, guys, something that's pretty important. I've kind of talked about it already, but I'm going to talk about it again because it's that very important. But it's the gram to mole conversions that we start to do a lot in the stoichiometry chapter, and we look at reactions. Because a lot of people will come to me and they'll say, I'm having trouble with all this reaction stuff, stoichiometry stuff, which I'll do some more of those probably next time. But the gram to mole conversions that we do at the start of the reaction chapter, but back up a minute. The people who are having trouble, always tell them, how are you doing, or how did you do with the chapter 1 conversions? And if they say, well, I got those, no problem, well, then you really need to work hard at seeing how the stuff in the conversions in chapter 1 and the conversions in the reaction chapter are really the same conversions. In fact, the reaction conversions are arguably easier because in chapter 1, you can pretty much any conversion, usually non-chemical, problem gets thrown your way. Meters to miles, grams to pounds, this to that. And like we saw earlier in the season, sometimes I just make up conversions for my problems, especially online. So you can't just say, hey, Google, and it tells you. But in the reaction chapter, you're really only you start off doing 3 conversions, really. Gram to mole using molar mass, Avogadro's number, which takes you from moles to individual, and mole to mole conversions. Atoms to formulas, or once we get into stoichiometry, moles of one thing in a reaction to moles of another thing in a reaction. So once we actually start doing the chemical conversions, we're only really doing 3 conversions over and over and over again. And really, once we get into reactions, we're doing 2 because we don't do a lot with the Avogadro's conversions. We usually stick on the mole scale. We don't do much on the individual atom molecule scale. And in the next chapter in solutions, we maybe add 1 more conversion on top of that. And the next chapter, maybe 1 more. But it's still conversion math with just a handful of conversion factors that you do over and over and over and over again. So to kind of see how that's true, I'm going to do some conversions from chapter 1. Then I'm going to do a very similar conversion from chapter 4, just so you can see that they're the same conversion. Excuse me, a little burp there. Probably shouldn't drink. That's why you don't drink beer during a I almost said podcast. This isn't a podcast. YouTube cast, Tubecast, Ucast, stupid TV show and hangout. I don't know. But anyway, let's look at our first example. So let's say, in chapter 1, you were asked to convert 20 miles to kilometers. No problem, some people think. You just look and you find a conversion factor, and it usually is that a mile is 1.609 kilometers. So you start with the unit that was given. You set up your conversion factor like a fraction, so the unwanted unit drops out at 32.2 kilometers. You move on to chapter 4. You might be asked to convert 20 moles of carbon to grams. But in that case, your conversion factor is carbon's molar mass. So that means that 1 mole of carbon is 12.01 grams, just like a mile equal a little over a mile and a half or kilometer and a half. So again, you start with what's given and you situate your conversion factor in a way that gets rid of the unwanted unit. And in this case, you get 240 grams. So again, you look at the two problems, they're very, very similar. You just take your conversion factor and situate it in a way that gets rid of the unit you don't want, whether you're going from miles to kilometers or moles to grams. And once we start doing the reaction math, anytime you want to go between grams and moles, you use molar mass. Either the molar mass of an element, or we'll see in a second, the molar mass of a whole compound. Same stuff, just different chemical. All right, so looking at another example. Oh, actually, I forgot there was an animation I didn't do. So what? Anyway, look at another conversion. Say apples cost $2.30 a dozen. Do they? I don't know. I hope I'm about right. Let's say you want to know how much 135 apples cost because you really like apples. So yeah, you start off with the unit you're given, if you consider apples a unit. You know, treat it like a dimensional analysis problem. The cost is per dozen, but you have a dozen of anything. You have 12 of that many things. So that gets rid of the individual apple unit. And if it's $2.30 per dozen, you set it up that way and the dozen unit drops out, giving you your answer. In chapter 4, you might see a really similar problem where carbon dioxide is 44.01 grams per mole. And you want to see how much 3.2 times 10 to the 24 CO2 molecules weigh. It's a lot bigger number because a molecule is a lot smaller than an apple. But other than the ridiculous size of that number, under normal conditions, it's ridiculous. You start with the number that's given. Apples, molecules, whatever. All right. A dozen is 12. A mole is Avogadro's number, 6.02 times 10 to the 23. If you set it up that way, the unwanted unit drops out. And just like your apples were $2.30 a dozen, carbon dioxide is 44.01 grams per mole. And if you write it this way, again, the unwanted unit drops out. And that gives you your answer of 234 grams. So again, just kind of compare the two types of problems from chapter 1 and the reaction chapter and just see how this conversion is the identical type of conversion as that one. They're the same conversion. See, that's the little highlight thing I meant to do here, but I forgot to do the highlight. And this conversion is the same as this conversion. Fun with PowerPoint animations. So again, if you're stuck with the chapter 4 math, go back and review the chapter 1 math. And if you're really comfortable with that, again, it's the same math. One thing I always tell my students, and in lecture, I just keep, in class lecture, I just beat it in their head over and over again. Don't let the chemistry throw you. When you do percent composition stuff that you might have done earlier, finding an empirical formula, it's just percent math. All these gram to mole conversion, it's conversion math. And again, the whole idea behind the conversion math is you set up the unwanted units and the multiplication division takes care of itself. Whether you're dealing with grams or pounds or meters to kilometers, whatever made up unit I did in the first episode. It's same math, different problem. Right. So moving on to the general 2 guys. With you guys, I thought I'd do a little bit of kinetics because this is about the time most folks are into kinetics. And one concept you guys are taught is usually how to determine a rate law by the initial rate method. And the initial rate method, all it really is just your simple, classic control variable type of experiment. Now, if you want to figure out the rate law of a reaction, you do the reaction once and you measure the rate. Then you do it again and you change one reactant, but you keep everybody else the same, constant variable. And you do it again, make another thing your constant, something else a variable, until you've looked at every reactant. So, for example, looking at, where'd he go? There he goes. That ain't it. Did I not? Oh, there we go. For example, let's look at, it's the same one, that's why. All right. Had them both on the same slide, sorry. For example, looking at problem P5 in my textbook, cheap plug. I have this one reaction, and here's a table of data. This time we did 3 trials, and you can see that you do it once with them both at 0.05. You do it again, you hold the NO concentration constant, but you change the chlorine concentration. So if the rate changes, then whatever's affecting the rate must be the thing you're changing, the chlorine. Then you do it again and you flip it around, keep the chlorine constant and change the NO and see how it affects your rate. So the first thing the question asks is to figure out the order with respect to NO. So to do this, again, you want to find a trial where you're keeping chlorine constant, which would be trials 1 and 3. So it looks like you're tripling the concentration of NO. And if you look at what's happening to the rate, it looks like the rate's going 1.2, 3.6. That looks like a triple as well. So remember, the rate and the concentration, they're proportional to each other to some factor X or order X. And in this case, if tripling the concentration triples the rate, then it must be first order with respect to this reactant. Because whatever you do to the concentration, it's the same effect on the rate. So it looks like we're first order with respect to NO. Next, we'll try to find the order with respect to chlorine. So again, you try to find trials where the other guy is being held constant and you're changing the one that you're interested in. And usually for Gen Chem, the way it's usually set up is you look for doubles or triples or some nice even multiple that you can sort of compare to. Usually that's how it's set up. Like here you compare trials 1 and 2, concentration of your nitrogen monoxide is being held constant, but we're changing the concentration of chlorine. Looks like we're doubling the concentration. The effect on the rate, you divide one by the other, it looks like you're quadrupling the rate when you double the concentration. So again, the two terms are rate and concentration. They're proportional to each other by some order X, with respect to the concentration of chlorine. Rate is proportional to the concentration of chlorine to some value X. And in this case, it looks like X is 2. It's a squared, because whatever you do to the concentration, the effect on the rate is that effect squared. So if you double it, you quadruple the rate. If you triple the concentration, the rate would increase by a factor of 8, if I remember my math. So you put the two together, first order with respect to NO, second order with respect to chlorine. You combine those two and change that to an equality by factoring in a constant. You get the rate law of your reaction. And finally, you can calculate the rate constant once you know the rate law. And the way you do that is you just pick any trial, because now you have, no matter, for any given trial, you have the rate and the concentration of everybody involved. So if you look at trial 1, you plug in that rate and those two concentrations, you have everything you need to solve for K. And if you want to check yourself, you can do the same thing with trial 2. And if you're really paranoid, you can triple check by plugging in your values from your last trial. And all three should agree with each other because that's how constants work, right? So for any initial rate method, that's usually how it's set up. And like I say, just be on the lookout for things like doubling and tripling or quadrupling like you saw there, because that's usually how they're set up. Unless your instructor is really being a little crab on you. Most book problems are set up that way anyway. So yeah, just make sure the other guy is being held constant, so you can see that, you know, if you're doubling this, what effect does that have on the rate? And one we didn't touch on a second ago was, you know, what if you double or triple or whatever the concentration and nothing happens to the rate? Well, remember in that case, you have what we call a zero order reactant. You know, zero order means that changing the concentration has no effect on the rate. So that is it for today. I will see you guys next time. Unless you thought I sucked, well, in that case, all right, have a good life. I don't know. There's plenty of other people out there that hopefully you can connect with, and the time that you and I had together, we'll just try to hold it into our hearts. And unless you just thought I was a prick, in that case, screw you. Just, you know, piss off. No, I'm kidding. Come back. No, seriously. Go your way. I'll go mine. Unless you really thought we had a cool thing going, then, you know, maybe we can kind of hang out next week. I don't know. Maybe. I don't know. I'm just going to drink.